This edition of SpaceTime is brought to you by Audible.com. Get a free audiobook download and a 30-day free trial at www.audibletrial.com/spacetime. Over 180,000 titles to choose from for your iPhone, Android, Kindle, or your MP3 player. That's audibletrial.com/spacetime for your free audiobook. This is SpaceTime Series 20, Episode 7, for broadcast on the 25th of January, 2017. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, solving a galactic murder mystery. Could there be life on Pluto? And work begins on NASA's Dark Energy Hunter. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has confirmed that young galaxies can be violently stripped of their youth and turned old by superheated intergalactic plasma contained in large halos of dark matter. The findings, reported in the monthly notices of the Royal Astronomical Society, mean a process known as ram pressure stripping is far more prevalent than previously thought. The study's lead author, Toby Brown from Swinburne University and the International Centre for Radio Astronomy Research, says the new findings help explain the process which appears to be killing off galaxies. The phenomenon, known as ram pressure stripping, drives gas from galaxies, sending them to an early death by depriving them of the material needed to make new stars. Brown and colleagues studied 11,000 galaxies, finding that ram pressure stripping was in fact occurring on a fairly widespread scale throughout the local universe. Galaxies are made of stars, which in turn are made from the collapse of giant clouds of molecular gas and dust. Astronomers have also concluded that galaxies are embedded in halos of dark matter. Dark matter is a mysterious invisible substance, which makes up about 74% of all the matter in the universe. What that means is that all the normal or baryonic matter, which makes up all the stuff on the periodic table, including all the stars, planets, asteroids, dogs, cats, cars, trees, houses, and even people, comprises just 26% of all the matter in the universe. Although astronomers have no idea what dark matter actually is, they know it exists because they can see its gravitational influence on normal matter. Brown says during their lifetimes, galaxies can inhabit dark matter halos of different sizes, ranging from masses typical for our own galaxy, the Milky Way, through to halos thousands of times more massive. As galaxies fall through these larger halos, the superheated intergalactic plasma between them removes all their gas in a fast-acting process called ram pressure stripping. Brown describes it as a sort of giant cosmic broom that comes through and physically sweeps gas from galaxies. And removing the gas from galaxies leaves them unable to form new stars. This process therefore dictates the life of the galaxy, because the existing stars will eventually cool off and grow old. So if you remove the fuel for new star formation, then you effectively kill the galaxy, turning it into a dying object. Astronomers already knew that ram pressure stripping affected galaxies in clusters, which are the most massive halos found in the universe. However, this new research shows that the same process is also operating on much smaller groups of just a few galaxies held together with much less dark matter. And the thing is, most galaxies in the universe live in these smaller galactic groups containing just a few large galaxies. Our own local group is a good example. It contains just two really big galaxies, the Milky Way and M31 Andromeda. To carry out the research, Brown and colleagues used an innovative technique combining the Sloan Digital Sky Survey, the largest optical galaxy survey ever completed, with the Arecibo Legacy Fast Alpha Survey, which is the largest set of radio observations looking at atomic gas in galaxies. Brown says the removal of gas by stripping is potentially the dominant way galaxies are quenched by their surroundings, meaning their gas is removed, forcing star formation to shut down. The other main process by which galaxies run out of gas and die is known as strangulation. Strangulation occurs when the gas is consumed to make stars faster than it's being replenished, so galaxies literally starve to death. But Brown says this is a slow-acting process, while what ram pressure stripping does is literally bop the galaxy on the head, removing its gas very quickly, in the order of just a few tens of billions of years. And astronomically speaking, that's incredibly fast.
What we're looking at is to understand why, when we look out into the universe, the populations of galaxies that we see generally fall into two camps. There are those that are star-forming and those that are not. So they're what we call alive and dead. So understanding how galaxies actually transition from this alive star-forming state into being these dead objects is what much of galaxy evolution, the topic that I study, is tied up in. So our paper was covering our result that showed that ram pressure stripping is causing much of the killing of these galaxies. So what ram pressure stripping is where the environment of the galaxy actually acts to drive the gas from it. So galaxies are defined as large collections of gas and stars, and they survive by converting that gas into stars. So if you have no gas because it's been driven out of the galaxy, you then shut down the star formation. This is not a new process, so to speak, but what we're showing is that it's more common than has previously been thought.
Are we talking environmental quenching here when one galaxy falls through the heart of a galaxy cluster, or is it mainly stellar winds, black hole winds, supernova events?
It's environmental quenching. It's a form of environmental quenching. So galaxies are not distributed evenly throughout the universe. What you have is large clusters of galaxies that have thousands of members, and then right the way down to isolated galaxies that exist on their own. Now, clusters of galaxies are very interesting and they're very extreme, but they're also quite rare. Most galaxies live in what we call groups, which is exactly as the name suggests, anything going from, say, 2 members up to several hundred. Now, we know in the extreme environment of the cluster, the temperatures of the gas that surrounds these galaxies is extremely hot. So when galaxies fall in through the cluster, this hot gas acts to sweep the gas out in ram pressure stripping. But what we're showing is that a fast-acting stripping process must also be acting way down into the group regime. And this is important because this is where most of the galaxies in the universe live.
So when we look at, say, a reddish-looking elliptical galaxy compared to a bright blue young spiral that's forming lots of stars, we see the difference between the two, and we assume that, oh, well, the elliptical galaxies, it's probably had a few collisions with other galaxies, but it's also probably just used up all its gas to make stars. There's more to it than that from what you're saying. This ram pressure stripping has a bigger impact.
Well, there is more to it. So there are many different mechanisms by which a galaxy may be quenched. So you can have, mergers, like you say, where two galaxies collide, and usually that results in an initial burst of star formation where essentially the gas in both those galaxies is compressed by the interaction, and a rapid conversion from gas into stars takes place. Then, because the gas is consumed, the stars grow old and the galaxy reddens. Now, the other processes that can occur are strangulation, whereby the gas supply to the galaxy, so it's what we call accretion, is cut off. So therefore, the reservoirs of gas that exist within it are not replaced as they're consumed by star formation, and this also is very prevalent. But what we're saying is that a significant proportion of these galaxies have to be quenched by a fast-acting process. And these fast-acting processes are essentially ram pressure stripping. And that's because starvation and also mergers to a lesser or greater extent, although the situation's not so clear with them, the starvation technique takes a long time to quench a galaxy because it has to use up its gas supply, its gas reservoir. But with ram pressure stripping, because you remove that gas reservoir instantaneously, astronomically speaking, you end up quenching the galaxy much faster. So actually that's the technique we used to figure out that it was ram pressure stripping that was responsible for this galaxy quenching. What we're showing actually is that galaxies with constant star formation rates, so say you take two galaxies and you plunge them into a group or a cluster, if their star formation rate remains relatively constant over a period of time, but their gas content is removed, this has to be ram pressure stripping, because with strangulation, their gas content would be consumed by that star formation over a much longer period.
You were also looking at the effect dark matter halos around galaxies had on all that.
Yes, exactly. So the way of quantifying where a galaxy lives in the universe is, well, there are many different techniques. One of the techniques and the approaches we used in this paper was to try and quantify just how much dark matter is residing around these galaxies and use that as a scale to determine how big and how important the environment is that's around them. And what we see is that as galaxies transition from smaller dark matter halos into the larger ones of bigger groups and clusters, what you then start to find is that this effect is more and more prevalent. And this makes sense, right? Because essentially what's doing the stripping is superheated gas or plasma that's in between these galaxies. Now, the way that gas gets heated is it gets accelerated by gravity, basically, to near relativistic speeds, to very, very fast speeds. And with great speed comes great temperature. So the more gravity you have, that comes from the mass. So the more mass, the more gravity, and then the hotter the gas is, the denser the gas is, and the more it can sweep the galaxies clean of their fuel for star formation.
And of course, most of the gravity is generated not by the matter you see in those galaxies, but by the dark matter halo that surrounds the galaxy or that emerges the galaxy.
Exactly. So of the entire mass energy budget of the universe, the kind of normal stuff that make up me and you and the Earth and the galaxies is only around 4 or 5%. Around 27% is dark matter, the rest being the mysterious thing we call dark energy.
Have you been able to use this at all to look at how the dark matter halos of different galaxies are interacting with each other, or if they're interacting with each other at all? That's got to be an interesting thing that's tickling you right now.
It's a very interesting field. It's a whole other field as to how dark matter interacts. I guess where this study falls and where my research falls is on that boundary between dark matter and normal matter. I want to understand how the amount and the nature of dark matter impacts the normal stuff that we can see, so the galaxies that we can see, and therefore dictates the evolution and the formation of these systems over time. To actually understand how dark matter interacts with dark matter is a whole field of almost theoretical physics on its own.
It is for now. Hopefully one day sooner won't be. When you look at small dwarf galaxies, they have proportionally far more dark matter compared to ordinary matter, baryonic matter, than larger galaxies like, say, the Milky Way or Andromeda. Does your work at all provide a clue as to why that's happening?
To be honest with you, no. So when you start getting into the dwarf regime, the normal relationships between say gas and stars, and also to some extent dark matter, they start to not behave in the same way that happens with the, shall we call it, kind of classical galaxy sizes that we look at. So we actually cut off, that's one of the reasons we cut off this study, so that we're looking at galaxies that are, say, 1 billion times the mass of our own sun, and not galaxies that are down into 1 million times the mass of our own sun, for instance.
I take it that's why you were quoting figures like galaxies may hang around in groups of 2. You're looking at things like our local group with Andromeda and the Milky Way, as opposed to, say, the 50, or if you believe cold dark matter, the hundreds of satellite galaxies that should be orbiting both the Milky Way and Andromeda.
Sure, exactly. So essentially it's a sensitivity issue in that, for example, if you put the local group system at a cosmological distance from us and try to observe it again, at some point you're only ever going to observe the 2 brightest members. So, and that effect is prevalent right the way through astronomy. If you want to be what we call representative, if you want to have a representative sample of galaxies above a given size, then you have to put in a mass cut. And this is what we do. We put in in a mass cut to ensure that we have a decent sampling of the galaxies around and above that mass limit.
Now, in order to do this work, you looked at data from the Sloan Digital Sky Survey, and also you looked at the Alpha Survey as well, the Arecibo Legacy Fast Alpha Survey.
Absolutely, yeah. These are the two respectively biggest optical with SDSS and biggest 21 centimeter, we call it, which is the radio wavelength that observes neutral hydrogen in galaxies. So that's the main component of the gas content of these galaxies. And so basically our approach is a statistical one. There is a lot of work looking at the effect of both environment and also other properties like stellar mass and star formation on the effect of the gas content. But the problem is that hydrogen emission is extremely faint. So this is why, for instance, you need huge survey dishes with very long integration times to observe these galaxies. And so what we wanted to do is say something statistical about the nature of gas removal in the universe. Was it prevalent on a widespread scale through the groups, or was it just affecting a few objects in the cluster, for instance? And so this is what we did. Our technique was to take the largest survey with the optical and the largest survey with the gas and put them together to see how many galaxies we could actually push down into observing.
In all, there was something like 11,000 galaxies involved in that.
So, yeah, in fact, the total sample for the volume we're looking at is more like 30,000 galaxies. But because we were interested in the impact of environment, we split them into different subcategories. And so in this particular study, we focused on what we call satellites, which is essentially if you have a group of galaxies, we define the most massive galaxy, so the brightest galaxy, if you like, as the central galaxy. And then within that group, every other member becomes a satellite, much like the moon to the Earth. Now, the reason we focused on the satellites is because they're expected to be the galaxies that are undergoing these types of processes. So they're the best places to try and figure out what's happening. The central galaxy sits at the bottom of the gravitational potential well, so it's much more likely to encounter things like a merger and starvation.
That's Toby Brown from Swinburne University and the International Centre for Radio Astronomy Research. I'm Stuart Gary. This is SpaceTime. A new study reported in the journal Nature ponders the possibility of life existing on the distant world of Pluto. NASA's New Horizons mission explored the dwarf planet and its system during an historic flyby in July 2015. Among the myriad of stunning discoveries about this remote and frozen world was evidence of a possible subsurface ocean beneath that heart-shaped region of Pluto known as Sputnik Planitia. One of the study's authors, Professor William McKinnon from the Washington University in St. Louis, who was part of the New Horizons science investigation team, says the existence of a subsurface ocean on Pluto is not so much a sign of liquid water as a tremendous clue that other dwarf planets in deep space could also harbour similar exotic oceans. And he says that naturally leads to the question of the possibility of life. Here on Earth, wherever liquid water exists, so does life. And so the search for life elsewhere in the universe centres around places where liquid water's been found. Pluto's subsurface ocean is calculated to be over 1,000 kilometres wide and up to 90 kilometres deep. But Pluto's ocean isn't just water, it's also laden with ammonia. The presence of this pungent, colourless liquid helps explain not only Pluto's orientation in space, but also the persistence of the massive ice-capped ocean, which other researchers call slushy, but which McKinnon prefers to depict as syrupy. Using computer models along with topographical and compositional data culled from New Horizons' Pluto flyby, McKinnon and colleagues examined Sputnik Planitia's churning nitrogen ice surface. McKinnon was also one of the authors studying the orientation and gravity on Pluto caused by this subsurface ocean. New Horizons also detected ammonia as a compound on Pluto's binary partner and largest moon Charon, and on one of Pluto's other smaller moons as well. McKinnon concludes all that means is that ammonia is almost certainly inside Pluto. He says that makes a rather noxious, very cold, salty and almost certainly very ammonia-rich syrupy ocean. Now, this is no place for microbes, much less fish, squid or any other life as we know it. But as with the methane seas on Saturn's largest moon, Titan, McKinnon says it raises the question of whether some truly novel life forms could exist in these exotic cold liquids. As humans explore deeper into the Kuiper Belt and consequently further from Earth, McKinnon thinks it could lead to the possible discovery of more such subsurface seas, and therefore more potential for exotic life. He says just from our samples here on Earth, we know life can tolerate all sorts of strange environments. It can handle a lot of salt, extreme cold, extreme heat, and even extreme toxicity and radiation. But he admits he doesn't think life could tolerate the amount of ammonia Pluto needs to prevent its ocean from freezing. See, ammonia is a really good antifreeze. Not that ammonia is all bad. Here on Earth, for example, there are microorganisms in the soil which fix nitrogen to ammonia, which is important for making DNA and proteins. McKinnon says if you're going to talk about life in an ocean that's completely covered with an ice shell, it seems most likely that the best you could hope for is some extremely primitive kind of organism. It might even be pre-cellular, which is what we think the earliest life on Earth may have been like. This newly published research also delves deep into the creation of the basin that includes the Sputnik Planitia. The basin was most likely formed when a 200-kilometre wide Kuiper Belt object slammed into Pluto more than 4 billion years ago. The collapse of the huge crater lifts Pluto's subsurface ocean and the dense water, combined with the dense surface nitrogen that fills the impact basin. It forms a huge mass excess that literally causes Pluto to tip over, reorienting itself with respect to its binary partner Charon. But that ocean uplift won't last if warm water ice at the base of the covering ice shell is able to flow and adjust itself in the way glaciers do here on Earth. However, if you add enough ammonia to the water, it can chill to incredibly cold temperatures down to minus 100 degrees Celsius and still be liquid, even if it does become quite viscous, a bit like chilled pancake syrup. At these temperatures, the water ice is rigid and the uplifted surface ocean becomes permanent. All these ideas about an ocean inside Pluto are creditable, but they're all inferences, not direct observations. McKinnon says if science really wants to confirm that such an ocean does exist on this dwarf planet, it would require gravity measurements or subsurface radar soundings, all of which could be accomplished only by a future orbiter mission to Pluto. And that means it'll be up to the next generation of scientists to pick up where New Horizons has left off. I'm Stuart Gary. You're listening to SpaceTime. Okay, time to take a quick break from the show and talk about one of our sponsors. Yeah, there are many times when you can't hold a book, but you can listen to one, such as when you're commuting, when you're at the gym, jogging, or walking the dog. And that's when I listen to Audible. It's my audio bookstore. And you know, I love the idea of someone reading to me. And no one offers a greater selection than Audible. In fact, they've got something like 180,000 titles plus to choose from. Audible's great if, like me, you have an unquenchable thirst for knowledge. Audible means you can learn so much. And right now, Audible has a special deal for SpaceTime listeners. Audible's offering a free audiobook download with a free 30-day trial to give you the opportunity to check out their service. And they've got so many great books to choose from. All the bestsellers, the classics, science fiction, science fact, history, biography, whatever, often from the people who actually wrote them. How about Born to Run by Bruce Springsteen, narrated by Bruce Springsteen? Or The Life of Keith Richards, narrated by Johnny Depp, Joe Hurley, and Keith Richards himself. No matter what your taste, there are over 180,000 titles to choose from. To download your free audiobook today, go to audibletrial.com/spacetime. That's audibletrial.com/spacetime for your free audiobook. Or just click on the link at spacetimewithstuartgary.com. And now, back to our show. NASA has announced plans for a new scientific instrument to study the mysterious force known as dark energy. Dark energy dominates the cosmos and will determine not just the universe's ultimate fate, but also how soon that happens. Astronomers have determined that some 68% of the mass energy budget of the universe is composed of dark energy. Just 27% is composed of an equally mysterious substance called dark matter, and only 5% is composed of normal or baryonic matter, the stuff that makes up the elements we see on the periodic table. Dark energy was first confirmed during the 1990s, when astronomers including Dr. Brian Schmidt from the Australian National University were studying exploding stars known as Type 1a supernovae. These thermonuclear events signal the destruction of a white dwarf star. They all explode with about the same mass, which is roughly 1.4 times the mass of the Sun, a figure known as the Chandrasekhar limit. Because they all explode with about the same mass, they all end up with about the same level of luminosity when they erupt. And so, by using the inverse square law, astronomers can determine how far away they are based on how bright they appear. Using these observations, Schmidt and colleagues were able to conclude that the universe's rate of expansion out from the Big Bang 13.8 billion years ago is increasing at an accelerating rate. It was Albert Einstein who first noticed the effects of dark energy in his field equations for his general theory of relativity over 100 years ago. The problem is, back then, scientists all thought the universe was in a constant, unchanging, steady state. In other words, the universe was static. But when Einstein developed his theory for general relativity, his calculations clearly showed an unstable equilibrium state for the cosmos. Any slight unevenness would cause the space-time fabric of the universe to expand or contract. And so Einstein introduced a fudge factor into his calculations, which he called the cosmological constant, represented by the Greek symbol lambda, which could, if needed, be added to the end of an equation to bring the universe back into a steady state. Years later, in 1929, Edwin Hubble saw that distant galaxies were all moving away from us, and that rate of recession was based on how far away the galaxies were. This led Albert Einstein to understand that his original equations were right. There was no need for a cosmological constant. He's later alleged to describe the cosmological constant as his biggest blunder. However, in 1998, the discovery that the universe's rate of expansion is accelerating means not just that Albert Einstein's cosmological constant is real, but rather than being zero as expected, it must have a slight positive value. Understanding how much dark energy there is in the universe and how strong it is vital for understanding the ultimate fate of the universe itself. You see, too little dark energy and gravity could take over, eventually stopping and reversing the expansion of the universe. That would ultimately result in the universe starting to contract. Eventually, that could result in a cataclysmic big crunch, destroying the cosmos. But with just the right amount of dark energy, the expansion of the universe could eventually coast to a standstill, giving us the steady-state static universe scientists believed 100 years ago. However, if our current understanding of dark energy strength is correct, then the universe will continue expanding forever. Eventually, all the stars and all the galaxies will disappear from our view beyond the cosmic horizon, leaving the universe cold, dark and empty, what astronomers call the Big Freeze. But if dark energy continues to increase in strength, then we face an even more horrific fate. Not only will the universe continue to expand on cosmic scales, but that expansion will eventually also happen on smaller local scales as well, even down to molecules and atoms being torn apart at the subatomic level in what astronomers refer to as the Big Rip. And the stronger the dark energy force, the sooner the Big Rip will happen. To better understand dark energy, Lockheed Martin and NASA are developing a new instrument assembly which could become the core of the primary scientific instrument aboard NASA's new Wide-Field Infrared Survey telescope, WFIRST. WFIRST's mission aims to uncover hundreds of millions of galaxies, revealing the physics that shapes them. As part of that project, scientists and engineers are working to develop a new dark energy instrument known as the Wide Field Optical Mechanical Assembly, or WOMA. WOMA will comprise the major portion of the scientific components on one of the two instruments aboard the telescope. It's based on Lockheed Martin's near-infrared camera, which will form the primary optical instrument for NASA's James Webb Space Telescope, designed to eventually replace the Hubble Space Telescope. The James Webb Space Telescope is slated for launch on a European Space Agency Ariane 5 rocket next year. The wide-field instrument on WFIRST will be a powerful optical payload with a massive focal plane array some 200 times larger than that on the James Webb Space Telescope. It will allow scientists to capture what some liken to panoramic images of the star field. In addition to dark energy research, WOMA will also use microlensing to complete a census of known exoplanets. Microlensing takes advantage of brief distortions in space caused by the mass of a foreground object to bend light and reveal new planets around distant stars. WFIRST's wide field of view will allow scientists to monitor some 200 million stars every 15 minutes for more than a year. When NASA finally launches WFIRST in the mid-2020s, it'll work in concert with other observatories to search new places and forces across the universe. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.